Numbers are everywhere, etched into the fabric of our universe. Some behave predictably, following clear patterns, but others remain stubbornly elusive. Among these, prime numbers stand as the ultimate enigma. Simple in definition, divisible only by one in themselves, yet their behavior defies logic, teasing mathematicians with mysteries that stretch back centuries. One of those mathematicians is James Maynard, a thinker who tackles problems that are deceptively simple to state, yet notoriously difficult to prove. From the hidden structure of prime gaps to the strange question of whether an infinite number of primes can exist without a specific digit, his work has changed how we understand the building blocks of numbers. This is his story. A tale of curiosity, defiance, and a relentless pursuit of mathematical truth. James Maynard wasn't your typical math prodigy. He didn't dazzle teachers with lightning-fast calculations or memorize endless formulas. Instead, he was the child who asked too many questions, the one who refused to accept things just because they were supposed to be true. Born in Chelmsford, England, Maynard displayed an early skepticism of authority. At just 3 years old, during an assessment by a health visitor, he deliberately answered questions incorrectly just to see how the adult would react. As a teenager, he once protested his school's grading system by writing only the correct answers to physics problems without explanations, knowing full well it would cost him points. After excelling in mathematics at King Edward VI Grammar School, Maynard continued his studies at Cambridge University, where he completed his bachelor's and master's degrees. He then pursued his PhD at Oxford University under the supervision of Roger Heath Brown, one of the leading figures in analytic number theory. At Oxford, he quickly gained a reputation for his deep insights into prime numbers, impressing his peers and mentors alike. After his doctoral studies, Maynard took on a postdoctoral research position at the University of Montreal, where he refined his ideas on prime gaps. During this period, he independently developed a sieve method that dramatically improved the bounds established by Yi Tang's breakthrough work on small gaps between primes. His results stunned the mathematical community and led to numerous invitations to prestigious institutions, solidifying his status as one of the most promising young mathematicians of his time. During this time, Maynard worked in near isolation, refining his methods for months before revealing his findings. He would later recall that the thrill of uncovering deeper truths about primes kept him working late into the night, often losing track of time completely. His postdoctoral advisor initially discouraged him from focusing so intently on prime gaps, believing the problem to be nearly intractable. Yet, Maynard's stubborn determination led him to an independent breakthrough that rivaled Zhang's work. His growing reputation soon landed him opportunities at Oxford University, where he took on a fellowship at Magdalen College. His time at Oxford cemented his place in the field, and it was there that he tackled another unusual question: whether an infinite number of primes could exist that entirely avoid a specific digit. His research on digit-restricted primes stunned even the most seasoned number theorists, showcasing his ability to transform seemingly simple problems into profound mathematical discoveries. To most, prime numbers seem scattered randomly across the number line, yet mathematicians suspect that within their chaotic distribution lies a hidden order, one that, if unlocked, could transform number theory. Number theory is the study of whole numbers and their relationships, and within this field, prime numbers hold a special significance. They are the building blocks of arithmetic, forming the foundation upon which all other numbers are constructed. Every integer can be expressed as a product of prime numbers in a unique way, a principle known as the fundamental theorem of arithmetic. Beyond their theoretical importance, primes play a crucial role in modern technology. Cryptography, the science of secure communication relies on the difficulty of factoring large prime numbers. Many encryption systems, including those used for online transactions, data protection, and cybersecurity, hinge on the difficulty of factoring large numbers into their prime components, a problem that remains computationally hard. Understanding primes also impacts pure mathematics, particularly in proving conjectures about the distribution of numbers. Questions like the twin prime conjecture and the Goldbach conjecture have tantalized mathematicians for centuries, and even small advances in understanding primes can yield breakthroughs across multiple fields of mathematics and computing. James Maynard's work focuses on unraveling these mysteries, shedding new light on patterns that had long been considered impenetrable. This is where James Maynard comes in. His fascination with primes led him to tackle some of the deepest, long-standing puzzles in mathematics, starting with one of the biggest, prime gaps. The twin prime conjecture suggests that there are infinitely many pairs of primes that are just two numbers apart, like 11 and 13 or 17 and 19, but proving this has eluded mathematicians for centuries. In 2013, Yitong Zhang shocked the math world by proving that infinitely many primes exist at most 70 million apart. It was an enormous breakthrough, but could the gap be reduced further? Enter Maynard. Within months, he independently devised a more powerful sieve method, bringing the bound down to 600, a dramatic improvement over Zhang's result. Unlike traditional sieve methods that relied heavily on optimizing existing frameworks, Maynard introduced a multidimensional sieve that allowed for greater flexibility in capturing prime pairs. His approach refined sieve theory by improving how prime clusters are weighted and analyzed, leading to more efficient methods for detecting small gaps between primes. His breakthrough was so elegant and adaptable that it led to new discoveries, eventually helping mathematicians push the bound to just 246. Maynard had made his mark, but he wasn't done yet. Some questions in math seem almost absurdly simple. Here's one. Are there infinitely many prime numbers that don't contain the digit 7? At first glance, this sounds trivial. Of course, there are primes without a 7. But as numbers grow larger, avoiding a specific digit becomes increasingly difficult. And proving that this pattern continues indefinitely, that was an unsolved problem for decades. Maynard proved that there exist infinitely many prime numbers that avoid a given digit, resolving a long-standing question in number theory. His proof not only solved this long-standing question, but also opened new doors in understanding the structure of prime numbers. Beyond prime numbers, Maynard has also made significant contributions to Diophantine approximation, a branch of number theory concerned with how well irrational numbers can be approximated by rational ones. His work in this area, particularly in proving refinements to the Duff-Schaeffer conjecture, has deepened our understanding of how rationals are distributed relative to irrationals. By developing new probabilistic methods, he helped resolve an 80-year-old question about which sequences of denominators allow for the best approximations, an achievement that further cements his place as one of the leading minds in modern number theory. Prime numbers underpin some of the most vital systems in modern life. Maynard's work has far-reaching consequences. Take cryptography and cybersecurity. The security of online transactions, encrypted messages, and even national security protocols all depend on prime numbers. Understanding their distribution can strengthen encryption techniques, making data even more secure. Improving our understanding of randomness has an impact on AI. Many artificial intelligence algorithms rely on random number generation, which, in turn, depends on prime numbers. Maynard's work on prime gaps helps refine these systems, making them more efficient. The behavior of prime numbers also has surprising parallels with quantum wave functions. As quantum computing advances, insights from number theory could play a role in developing new quantum algorithms. Maynard's discoveries don't just solve math problems, they reshape our understanding of numbers, with implications far beyond pure mathematics. Despite his brilliance, James Maynard isn't the stereotypical isolated mathematician. He's sociable, outgoing, and known for his love of photography, capturing patterns in cityscapes, much like he does in numbers. His colleagues describe him as a central figure in modern number theory, but also as someone who remains humble and approachable. He has a habit of forgetting his glasses, once mistook a stranger for his girlfriend, and yet, when it comes to mathematics, his focus is razor-sharp. Maynard's work on prime gaps, digit-restricted primes, and number theory has reshaped mathematics. But the most exciting part? There are still countless unanswered questions in number theory, waiting for someone to unlock their secrets. Maynard's journey proves that curiosity, persistence, and unconventional thinking can lead to breakthroughs in even the most perplexing problems. Who knows? The next great discovery in mathematics might come from someone asking the simplest of questions, just as he once did.